Question 141. Your company is developing a web-based application. You need to make sure that production deployments are linked to source code commits and are fully auditable. What should you do? A. Make sure a developer is tagging the code commit with the date and time of commit. B. Make sure a developer is adding a comment to the commit that links to the deployment. C. Make the container tag match the source code commit hash. D. Make sure the developer is tagging the commits with latest. The best option is option C. Make the container tag match the source code commit hash. Explanation. To ensure that production deployments are linked to source code commits and are fully auditable, it is crucial to use a container tag that directly corresponds to the source code commit hash. This ensures that the deployed version of the application can be traced back to the exact source code that was used to build it, providing clear traceability and auditing capabilities. By using commit hashes as container tags, you eliminate ambiguity and make it easy to track the precise version of the application deployed in production. Why other options are less suitable? Option A suggests tagging the code commit with the date and time of the commit. While this provides a timestamp, it doesn't link directly to the deployment, and it's not as reliable for tracing specific changes, especially when multiple commits occur in a short time frame. Option B suggests adding a comment to the commit that links to the deployment. While this can be useful, it requires manual intervention and doesn't automatically create a link between the code and the deployment. Additionally, it's less scalable and prone to human error. Option D suggests tagging the commits with latest. This approach is not recommended because the latest tag can be ambiguous and doesn't provide a direct link to a specific commit or version of the source code. This can cause issues with tracking and auditing, especially if multiple versions of the application are deployed over time. Conclusion. Option C is the most reliable and auditable approach. By using the source code commit hash as the container tag, you ensure that each deployment is tightly coupled with the exact code version that was deployed, providing full traceability and making the process more transparent and verifiable. Question 142. An application development team has come to you for advice. They are planning to write and deploy an HTTPS API using Go 1.12. The API will have a very unpredictable workload and must remain reliable during peaks in traffic. They want to minimize operational overhead for this application. Which approach should you recommend? A. Develop the application with containers and deploy to Google Kubernetes Engine. B. Develop the application for App Engine standard environment. C. Use a managed instance group when deploying to Compute Engine. D. Develop the application for App Engine flexible environment using a custom runtime. The best option is option B. Develop the application for App Engine standard environment. Explanation. App Engine standard environment is fully managed by Google Cloud, which minimizes operational overhead. It is designed for applications with unpredictable traffic patterns and offers automatic scaling to handle peaks in traffic, ensuring reliability without the need for manual intervention. App Engine takes care of the infrastructure management, scaling, patching, and load balancing, which means the development team can focus purely on writing and deploying the application code. Why other options are less suitable? Option A. Develop the application with containers and deploy to Google Kubernetes Engine. While Kubernetes Engine offers flexibility and scalability, it requires more operational overhead. The development team would need to manage the cluster, scaling, and other infrastructure-related tasks. If minimizing operational overhead is a priority, Kubernetes Engine might not be the best choice for this scenario. Option C. Use a managed instance group when deploying to Compute Engine. A managed instance group, MIG, provides automatic scaling, but managing and maintaining Compute Engine instances still involves more operational overhead compared to App Engine, especially when considering tasks like updates, scaling configuration, and infrastructure management. Option D. Develop the application for App Engine flexible environment using a custom runtime. While the flexible environment also supports custom runtimes and automatic scaling, it involves more complexity compared to the standard environment. The flexible environment provides more flexibility in terms of runtime, but if the workload is unpredictable, the standard environment is typically the simpler and more cost-effective option. Conclusion: Option B is the best choice because it offers automatic scaling, is fully managed, and minimizes the operational overhead that the development team would have to handle. It is the most efficient option for applications with unpredictable workloads that require minimal maintenance and high reliability during traffic peaks. Question 143. Your company is designing its data lake on Google Cloud and wants to develop different ingestion pipelines to collect unstructured data from different sources. After the data is stored in Google Cloud, it will be processed in several data pipelines to build a recommendation engine for end users on the website. The structure of the data retrieved from the source systems can change at any time. The data must be stored exactly as it was retrieved for reprocessing purposes in case the data structure is incompatible with the current processing pipelines. You need to design an architecture to support the use case after you retrieve the data. What should you do? A. Send the data through the processing pipeline, and then store the processed data in a BigQuery table for reprocessing. B. Store the data in a BigQuery table. Design the processing pipelines to retrieve the data from the table. C. Send the data through the processing pipeline, and then store the processed data in a cloud storage bucket for reprocessing. D. Store the data in a cloud storage bucket. Design the processing pipelines to retrieve the data from the bucket. The best approach is option D, store the data in a cloud storage bucket. Design the processing pipelines to retrieve the data from the bucket. Explanation: Cloud storage is the most suitable storage option for unstructured data that might change in structure over time. It allows you to store data in its raw form without any transformation, which is crucial when you need to ensure the data is stored exactly as it was retrieved for future reprocessing. Cloud storage is also highly durable, scalable, and cost-effective for large volumes of data. Why other options are less suitable? Option A, send the data through the processing pipeline, and then store the processed data in a BigQuery table for reprocessing. While BigQuery is great for analyzing structured data, it is not the best option for storing raw, unstructured data. BigQuery tables require a well-defined schema, and managing schema changes could be complex when dealing with unstructured data. This option does not fulfill the requirement to store the data exactly as retrieved, as the data will be transformed during the pipeline process. Option B, store the data in a BigQuery table. Design the processing pipelines to retrieve the data from the table. Similar to option A, this option would require transforming the raw data into a structured format before storing it in BigQuery. BigQuery is more suited for structured data and doesn't provide a straightforward method for handling evolving data schemas in a flexible, raw form. It would not meet the requirement of storing data exactly as retrieved. Option C, send the data through the processing pipeline, and then store the processed data in a cloud storage bucket for reprocessing. This option involves transforming the data during the pipeline process, which contradicts the need to store the raw, unstructured data for reprocessing. The raw data must be preserved in its original form, which would be lost in this step. Conclusion: Option D is the best choice because it allows you to store unstructured data in cloud storage in its raw form, providing flexibility for handling changing data structures and the ability to reprocess the data later without transformations. It is also cost-effective and scalable, making it ideal for a data lake architecture. Question 144. You are responsible for the Google Cloud environment in your company. Multiple departments need access to their own projects, and the members within each department will have the same project responsibilities. You want to structure your Google Cloud environment for minimal maintenance and maximum overview of IAM permissions as each department's projects start and end. You want to follow Google recommended practices. What should you do? A. Grant all department members the required IAM permissions for their respective projects. B. Create a Google group per department and add all department members to their respective groups. Create a folder per department and grant the respective group the required IAM permissions at the folder level. Add the projects under the respective folders. C. Create a folder per department and grant the respective members of the department the required IAM permissions at the folder level. Structure all projects for each department under the respective folders. D. Create a Google group per department and add all department members to their respective groups. Grant each group the required IAM permissions for their respective projects. The best approach is option B. Create a Google group per department and add all department members to their respective groups. Create a folder per department and grant the respective group the required IAM permissions at the folder level. Add the projects under the respective folders. Explanation. This approach follows Google recommended practices for managing IAM permissions at scale. By creating a Google group for each department, you can easily manage access by adding or removing members from the group, which eliminates the need to modify IAM roles directly on individual projects. Creating a folder per department allows you to manage IAM permissions at a higher level, the folder level, ensuring that all projects under the folder inherit the permissions automatically. This method reduces the administrative burden of managing permissions individually for each project and provides a clear overview of access controls across departments. Why other options are less suitable? Option A. Grant all department members the required IAM permissions for their respective projects. This approach can become cumbersome as the number of departments and projects increases. Managing IAM permissions on a per-project basis does not provide an overview of who has access to what, and it becomes harder to scale as more projects are added or removed. Option C. Create a folder per department and grant the respective members of the department the required IAM permissions at the folder level. Structure all projects for each department under the respective folders. While this approach is better than granting IAM permissions at the project level, it is not as efficient as using Google Groups. Directly assigning IAM roles to individual members at the folder level can become difficult to manage, especially as team members join or leave. Using Google Groups for departments ensures more centralized and flexible permission management. Option D. Create a Google group per department and add all department members to their respective groups. Grant each group the required IAM permissions for their respective projects. This approach could be valid, but it involves granting IAM permissions at the individual project level rather than at the folder level. While Google Groups simplify member management, granting permissions on a per-project basis is more cumbersome than assigning them at the folder level, especially when you want a high-level overview of access control. Conclusion. Option B is the best choice as it leverages both Google Groups and folder-level IAM permissions, minimizing maintenance while providing a scalable and manageable solution for large environments. It aligns with Google recommended practices for organizing and managing IAM in cloud environments. Question 145. Your company has an application running as a deployment in a Google Kubernetes Engine (GKE) cluster. You have separate clusters for development, staging, and production. You have discovered that the team is able to deploy a Docker image to the production cluster without first testing the deployment in development and then staging. You want to allow the team to have autonomy but want to prevent this from happening. You want a Google Cloud solution that can be implemented quickly with minimal effort. What should you do? A. Configure a Kubernetes lifecycle hook to prevent the container from starting if it is not approved for usage in the given environment. B. Implement a corporate policy to prevent teams from deploying Docker images to an environment unless the Docker image was tested in an earlier environment. C. Configure binary authorization policies for the development, staging, and production clusters. Create attestations as part of the continuous integration pipeline. D. Create a Kubernetes admissions controller to prevent the container from starting if it is not approved for usage in the given environment. The best approach is option C. Configure binary authorization policies for the development, staging, and production clusters. create attestations as part of the continuous integration pipeline. Explanation. Binary authorization is a Google Cloud feature that helps enforce deployment policies and ensures that only trusted images are deployed to your clusters. By configuring binary authorization, you can control which images are allowed to be deployed in each environment, ensuring that images are properly tested in development and staging before being deployed to production. This method integrates seamlessly with your continuous integration pipeline, where attestations, i.e., signatures or validations, can be added to verify that the image passed necessary tests in earlier environments before being deployed to production. This solution can be quickly implemented and requires minimal operational overhead, making it a strong fit for your requirements. Why other options are less suitable? Option A. Configure a Kubernetes lifecycle hook to prevent the container from starting if it is not approved for usage in the given environment. While Kubernetes lifecycle hooks can manage container behavior during startup or shutdown, they are not the right tool for enforcing deployment policies in a multi-environment setup. Lifecycle hooks are more focused on managing the internal state of containers rather than controlling the deployment pipeline across different environments. Option B. Implement a corporate policy to prevent teams from deploying Docker images to an environment unless the Docker image was tested in an earlier environment. While policies can help guide behavior, they are not an enforceable technical solution. This approach relies on manual discipline and does not prevent the team from bypassing the process. Automation via tools like binary authorization provides stronger guarantees. Option D. Create a Kubernetes admissions controller to prevent the container from starting if it is not approved for usage in the given environment. An admission controller can be used to enforce policies within Kubernetes, but it requires more setup and complexity compared to binary authorization. It can prevent containers from being deployed, but it's typically better suited for more specific policy enforcement at the cluster level rather than as part of a broader CI/CD pipeline. Conclusion. Option C is the best choice because it directly addresses the issue with a minimal effort solution by automating deployment policies via binary authorization, ensuring that images are properly validated in each environment before being allowed in production. This solution provides control while allowing the team autonomy in managing deployments. Question 146. Your company wants to migrate their 10 terabits on-premises database export into cloud storage. You want to minimize the time it takes to complete this activity, the overall cost, and database load. The bandwidth between the on-premises environment and Google Cloud is 1 gigabit per second. You want to follow Google recommended practices. What should you do? A. Develop a data flow job to read data directly from the database and write it into cloud storage. B. Use the data transfer appliance to perform an offline migration. C. Use a commercial partner ETL solution to extract the data from the on-premises database and upload it into cloud storage. D. Compress the data and upload it with XUTIL-M to enable multi-threaded copy. The best option is option B. Use the data transfer appliance to perform an offline migration. Explanation. The data transfer appliance is a physical device provided by Google Cloud that allows for the offline migration of large data sets from on-premises to Google Cloud. It is ideal for situations where you have large data sets, like your 10 terabits database export, and want to minimize the time and cost involved in transferring them over a network with limited bandwidth, 1 gigabit per second in your case. With the data transfer appliance, you can load the data onto the device locally, then ship it to a Google data center where it will be uploaded directly into cloud storage. This eliminates the dependency on your network speed and avoids overloading your database or affecting its performance during the migration process. Given that you have a large dataset and a relatively slow bandwidth connection, this option will be significantly faster and more cost-effective than transferring the data over the internet. Why other options are less suitable? Option A. Develop a data flow job to read data directly from the database and write it into cloud storage. While data flow can be used for transferring data, it would require network bandwidth for the continuous transfer of the database export. Given the large size of the data and your limited bandwidth, 1 gigabit per second, this could take a very long time and could impact your on-premises database performance. Option C, use a commercial partner ETL solution to extract the data from the on-premises database and upload it into cloud storage. Commercial ETL solutions may help with data extraction and transformation, but they still rely on network bandwidth for the transfer, which is not optimal for large datasets with limited bandwidth. This option might involve additional costs and complexity without providing the same performance benefits as the data transfer appliance. Option D, compress the data and upload it with XUTIL-M to enable multi-threaded copy. While using XUTIL with multi-threading can help speed up the transfer over the network, compressing the data and uploading it via the internet will still be bound by your available 1 gigabit per second bandwidth. With a 10 terabits dataset, this approach will still take a significant amount of time and can increase the load on your database, potentially affecting performance. Conclusion. Option B is the best choice because the data transfer appliance provides a highly efficient, cost-effective, and reliable way to transfer large datasets offline, bypassing the limitations of your current network bandwidth and minimizing the impact on your database. Question 147. Your company has an enterprise application running on compute engine that requires high availability and high performance. The application has been deployed on 2 instances in 2 zones in the same region in active-passive mode. The application writes data to a persistent disk. In the case of a single zone outage, that data should be immediately made available to the other instance in the other zone. You want to maximize performance while minimizing downtime and data loss. What should you do? A1. Attach a persistent SSD disk to the first instance. 2. Create a snapshot every hour. 3. In case of a zone outage, recreate a persistent SSD disk in the second instance where data is coming from the created snapshot. B1. Create a cloud storage bucket. 2. Mount the bucket into the first instance with GCS views. 3. In case of a zone outage, mount the cloud storage bucket to the second instance with GCS views. CA1. Attach a regional SSD persistent disk to the first instance. 2. In case of a zone outage, force attach the disk to the other instance. D1. Attach a local SSD to the first instance disk. 2. Execute an rsync command every hour where the target is a persistent SSD disk attached to the second instance. 3. In case of a zone outage, use the second instance. The best option is option C, attach a regional SSD persistent disk to the first instance. In case of a zone outage, force attach the disk to the other instance. Explanation. To achieve high availability and minimal downtime in case of a zone outage, you need a persistent storage solution that can be shared between 2 instances in different zones within the same region. A regional persistent SSD disk is designed for this exact use case. It replicates data across 2 zones, making it highly available and fault-tolerant. By attaching this regional SSD disk to the first instance, and in case of a zone outage, force attaching the same disk to the second instance, you can ensure that the data is immediately available to the second instance, minimizing downtime and data loss. Regional persistent disks automatically replicate data between 2 zones in the same region, providing high availability and consistency. This means that even if one zone experiences an outage, the second zone can access the data without additional setup or manual intervention, ensuring performance and availability. Why other options are less suitable? Option A, attach a persistent SSD disk to the first instance, create a snapshot every hour, and in case of a zone outage, recreate the disk from the snapshot. This option requires manual intervention to create snapshots and recreate disks. It also involves some downtime and potential data loss between the last snapshot and the recovery, which does not meet the goal of minimizing downtime and data loss. Snapshots are not an ideal solution for high availability in real-time applications where immediate failover is required. Option B, create a cloud storage bucket, mount the bucket with GCS views, and in case of a zone outage, mount the bucket to the second instance. Cloud storage is not designed to be a high-performance, low-latency disk solution for applications that require high availability. It is better suited for storing large datasets or objects. Using GCS views adds additional complexity and overhead, and may not provide the same level of performance required for your application, especially for transactional workloads that require high availability. Option D. Attach a local SSD to the first instance, execute an rsync command every hour to sync data to the second instance, and use the second instance in case of a zone outage. Local SSDs provide high performance but are not designed for high availability since they are attached to specific instances and cannot be easily shared across zones. Additionally, rsync is a manual process that requires scheduled execution and does not guarantee real-time data synchronization. This approach introduces complexity and potential data loss, as the synchronization may not be up to date at the time of a failure. Conclusion. Option C is the best solution because a regional persistent SSD disk ensures high availability and minimal downtime by automatically replicating data across two zones in the same region. This approach allows for immediate failover in case of a zone outage, with no manual intervention required, ensuring both high performance and data availability. Question 148. You are designing a data warehouse on Google Cloud and want to store sensitive data in BigQuery. Your company requires you to generate the encryption keys outside of Google Cloud. You need to implement a solution. What should you do? A. Generate a new key in Cloud Key Management Service, Cloud KMS. Store all data in cloud storage using the Customer Managed Key option and select the created key. Set up a data flow pipeline to decrypt the data and to store it in a new BigQuery dataset. B. Generate a new key in Cloud KMS. Create a dataset in BigQuery using the Customer Managed Key option and select the created key. C. Import a key in Cloud KMS. Store all data in cloud storage using the Customer Managed Key option and select the created key. Set up a data flow pipeline to decrypt the data and to store it in a new BigQuery dataset. D. Import a key in Cloud KMS. Create a dataset in BigQuery using the Customer Supplied Key option and select the created key. The best option is option C, import a key in Cloud KMS. Store all data in cloud storage using the Customer Managed Key option and select the created key. Set up a data flow pipeline to decrypt the data and to store it in a new BigQuery dataset. Explanation. The key requirement in this case is that the company needs to generate encryption keys outside of Google Cloud, which means Customer Managed Keys, CMK, are needed. Cloud KMS supports importing external keys, which is why option C is the best choice. Here's the detailed breakdown. Import a key in Cloud KMS. If you are generating encryption keys outside Google Cloud, Cloud KMS allows importing keys that have been created externally, making this option a suitable choice. You can use these keys to control encryption and decryption processes within Google Cloud. Store data in cloud storage. After importing the key, you store the sensitive data in cloud storage using the Customer Managed Key option, ensuring that the data is encrypted using the externally managed key. Data flow pipeline. A data flow pipeline can be set up to decrypt the data, if necessary, and then move the decrypted data to BigQuery, ensuring that the data is processed and stored securely within the data warehouse. This approach adheres to Google Cloud's best practices for data security, where sensitive data is encrypted using keys that are managed externally, ensuring compliance and control over the encryption process. Why other options are less suitable? Option A. Generate a new key in Cloud Key Management Service, Cloud KMS. Store all data in cloud storage using the Customer Managed Key option and select the created key. Set up a data flow pipeline to decrypt the data and to store it in a new BigQuery dataset. This option suggests generating a new key in Cloud KMS, but the company requires the encryption key to be generated outside of Google Cloud, which makes this option unsuitable because it doesn't meet the requirement to use an externally managed key. Option B. Generate a new key in Cloud KMS. Create a dataset in BigQuery using the Customer Managed Key option and select the created key. This option uses a key generated in Cloud KMS, which does not meet the requirement of using a key generated outside of Google Cloud. The company requires the encryption key to be created externally, so this option is also not suitable. Option D. Import a key in Cloud KMS. Create a dataset in BigQuery using the customer-supplied key option and select the created key. In this option, the customer-supplied key option is mentioned, which typically refers to using a raw key provided by the customer and not a fully managed key in Cloud KMS. BigQuery only supports the customer-managed key option, not customer-supplied keys, making this approach invalid for the use case. Conclusion. Option C is the best choice because it uses Cloud KMS to import externally generated encryption keys, stores sensitive data in cloud storage with customer-managed keys, and processes the data into BigQuery using a data flow pipeline, ensuring security and compliance with external key management requirements. Question 149. Your organization has stored sensitive data in a cloud storage bucket. For regulatory reasons, your company must be able to rotate the encryption key used to encrypt the data in the bucket. The data will be processed in Dataproc. You want to follow Google recommended practices for security. What should you do? A. Create a key with Cloud Key Management Service, KMS. Encrypt the data using the encrypt method of Cloud KMS. B. Create a key with Cloud Key Management Service, KMS. Set the encryption key on the bucket to the Cloud KMS key. C. Generate a GPG key pair. Encrypt the data using the GPG key. Upload the encrypted data to the bucket. D. Generate an AES-256 encryption key. Encrypt the data in the bucket using the customer-supplied encryption keys feature. The best option is option B. Create a key with Cloud Key Management Service, KMS. Set the encryption key on the bucket to the Cloud KMS key. Explanation. Google Cloud's best practice for managing encryption keys involves using Cloud Key Management Service, KMS. With Cloud KMS, you can create and manage encryption keys in a centralized manner. You can also rotate the keys for regulatory compliance, which is a key requirement in this scenario. Cloud KMS is a fully managed service, making it the ideal solution for handling encryption in a secure and efficient manner. By setting the encryption key on the cloud storage bucket to a Cloud KMS key, Google Cloud handles the encryption and key management for you, allowing the encryption key to be rotated easily while maintaining the security of the data. Key benefits of option B. Key rotation. Cloud KMS supports key rotation, which is necessary for compliance in regulatory scenarios. Centralized key management. Cloud KMS centralizes key management, making it easier to manage encryption across Google Cloud services. Integration with Google Cloud services. Cloud storage integrates natively with Cloud KMS, ensuring seamless encryption and decryption with minimal manual intervention. Security. Using Cloud KMS for encryption ensures that your data is encrypted with strong, Google-managed keys that meet security standards. Why other options are less suitable? Option A. Create a key with Cloud Key Management Service, KMS. Encrypt the data using the encrypt method of Cloud KMS. While this approach suggests using Cloud KMS, it focuses on manually encrypting the data via Cloud KMS rather than directly integrating it with cloud storage. The process would require more manual steps and does not leverage Google Cloud's native integration between cloud storage and Cloud KMS. Option C. Generate a GPG key pair. Encrypt the data using the GPG key. Upload the encrypted data to the bucket. This option requires using an external tool, GPG, for encryption, which complicates the process and adds operational overhead. It is not as seamless or as secure as using Cloud KMS, especially when it comes to managing key rotation and ensuring integration with Google Cloud services. Option D. Generate an AES-256 encryption key. Encrypt the data in the bucket using the customer-supplied encryption keys feature. Using customer-supplied encryption keys, CSEK, requires manual management of the keys, which adds operational complexity and risks related to key rotation, storage, and security. CSEK is suitable in some cases, but it is generally less efficient and scalable than using Cloud KMS. Conclusion. Option B is the best choice because it leverages Cloud KMS for key management, integrates seamlessly with cloud storage, and supports the key rotation required for compliance. This approach follows Google recommended practices for secure and efficient data encryption management. Question 150. Your team needs to create a Google Kubernetes Engine (GKE) cluster to host a newly built application that requires access to third-party services on the Internet. Your company does not allow any compute engine instance to have a public IP address on Google Cloud. You need to create a deployment strategy that adheres to these guidelines. What should you do? A. Configure the GKE cluster as a private cluster, and configure Cloud NAT gateway for the cluster subnet. B. Configure the GKE cluster as a private cluster. Configure private Google access on the Virtual Private Cloud, VPC. C. Configure the GKE cluster as a route-based cluster. Configure private Google access on the Virtual Private Cloud, VPC. D. Create a compute engine instance, and install a NAT proxy on the instance. Configure all workloads on GKE to pass through this proxy to access third-party. The best option is option A. Configure the GKE cluster as a private cluster, and configure Cloud NAT gateway for the cluster subnet. Explanation. Private cluster. When you create a private GKE cluster, the nodes in the cluster do not have public IP addresses, which is in line with your company's policy of not allowing compute engine instances to have public IPs. Cloud NAT gateway, Cloud NAT, Network Address Translation, allows the GKE nodes to access the Internet for outgoing traffic while still not having public IP addresses. This ensures that your GKE nodes can communicate with third-party services on the Internet without violating the no public IP policy. Compliance with company policy. Cloud NAT ensures that the GKE cluster can still access external resources while complying with the company's security policies, making this solution efficient and secure. Key benefits of option A. Private GKE cluster. The nodes in a private GKE cluster do not require public IP addresses, adhering to your company's requirement. Cloud NAT. This service enables secure Internet access from private IPs without exposing them publicly. It handles the egress traffic to external services, ensuring connectivity while maintaining security. Scalability and automation. Cloud NAT scales automatically with the traffic, and you don't need to manage any proxy instances, simplifying operations. Why other options are less suitable? Option B. Configure the GKE cluster as a private cluster. Configure private Google access on the Virtual Private Cloud, VPC. While private Google access allows instances without public IPs to access Google services, it does not provide access to third-party services on the Internet. This would only be suitable for accessing Google Cloud resources, not external Internet services. Option C. Configure the GKE cluster as a route-based cluster. Configure private Google access on the Virtual Private Cloud, VPC. This option is similar to option B and also fails to allow access to third-party services on the Internet. Route-based clusters are part of networking in GKE, but this configuration wouldn't allow access to external Internet services unless a NAT solution is implemented. Option D. Create a compute engine instance, and install a NAT proxy on the instance. Configure all workloads on GKE to pass through this proxy to access third-party services. While this option could work, it adds complexity and overhead. You would need to maintain the proxy instance, which introduces operational challenges. Using Cloud NAT, in contrast, is a fully managed service and is a more scalable and reliable approach. Conclusion. Option A is the best choice because it leverages a private GKE cluster and Cloud NAT to provide secure access to third-party services on the Internet while adhering to your company's security policies. This solution is more streamlined, scalable, and easier to manage than the alternatives.